what we're going to do is we're going to ask for a particular type of compactification of heterotic string theory to 4 dimensions. So we're going to look for compactifications of heterotic string theory to a 4-dimensional n equals 1 supersymmetric theory. So a 4-dimensional theory that has 4 supercharges. So we should start by saying what our starting point is, just to make sure we're all on the same page. It's always reassuring to see a Lagrangian, so you know what theory we're talking about. So the theory we're going to talk about is just lowest order alpha prime, so we take the string length to 0. It's just going to be this thing. So it's the usual Navier-Stokes sector heterotic string. We have just the Ricci curvature of an all 10-dimensional metric. We have a Dirac scalar field. And then we have H, which is going to be at this order satisfying the usual Bianchi identity, so it can be written locally at least as E of something, a 2 form. So I've written up an action. We're never actually going to use it. The reason we're not going to use it is what we're going to be interested in is the supersymmetry of solutions of this theory. And for most cases we look at, if you have a supersymmetric configuration for this theory, it will also solve the equations of motion given your constraints. So instead what we need is, if you take this action and you add on all the fermions, the formula writes down. If you take this action, it's invariant, the Bianchi identity are invariant under a set of supersymmetric transformations, and those are the things we actually need. So the Susy transformations for this action look like following. So first of all, I'm just going to write down fermionic transformations. We'll say what that is in a second. So the gravitational multiplet here has an associated fermion called the gravitino that also has a vector index. And it transforms as follows. That's the Levi-Strauss connection, and then just asymmetric product of gamma matrices contracted with this field string. And the supersymmetry parameters here, this fermionic parameter for the symmetry, is a 16-component spinor. So it's 16 component number on the bias 10 dimensions. Okay. What else do we have? At the level I'm working, we also have one more fermion field, which is called the Philipsino. And that has a similar transformation as d slash acting on phi, another one of these terms involving what are invariably called the flux, the H field. And again, a parameter. And there's another set of transformations for the bosons as well, and if you plug all of these into the action, it's invariant. Okay, where do we care? So we're going to be looking for n equals 1 configurations. So what type of solution to this theory will preserve n equals 1? Well, it's just like the Higgs effect in one of the engaged theories, right? If you start with some sg3 gauge group, say, and you have a Higgs vev in your vacuum, what is the unbroken part of the gauge group? Well, anything that leaves the Higgs vev alone, anything that commutes with the Higgs vev. And it's the same thing with supersymmetry, of course. If you have a background that you plug in here, a given metric and a given H field, what supersymmetry do you preserve? You preserve any of these 16 supercharges for which the change in the fields is 0, and the same for the bosonic fields. Because then the field configuration is being left in the transformation. The reason I'm written up the bosonic fields is just that if you have a boson variation of a boson, and you have a fermionic parameter, there must be at least one fermionic field on the right hand side, and all the fermions will be 0 in fact. So these bosonic variations are going to be tribute 0 for all supercharges. So what we have to do is look at these fermionic variations and ask, when do these fermionic variations preserve 4 out of these 16 supercharges? That's what n equals 1 supersymmetry is, 4 supercharges. Okay, to do that we're going to make an ansatz, and a typical ansatz you may make is the following. First of all, we want 4-dimensional space and we want a 6D compact space. So we're going to write our 10-dimensional manifold of some 4-dimensional piece, and for now let's just have a direct product with a 6-dimensional compact space. And we're going to take the 4-dimensional space to be maximally symmetric. Okay. So in particular, it's ADS, it's de Sitter, or it's Minkowski space. If we're going to make that ansatz for the metric, the other fields in theory, the dilaton and the B field, better also respect this symmetry. So to also maintain this 4-dimensional symmetry, we're going to take any component of the field strength with a 4D index. So let's just have throughout the lectures I and J run over 10D indices, A and B run over 60, and mu and U run over 40. Any component of the metric at all with 4-dimensional index is going to be 0, or it's going to pick out certain directions in 4-dimensional space. Okay. If likewise the derivative of phi, that will be 0 in 4 dimensions, because otherwise it will pick out a particular direction in 4-dimensional space. So this is our ansatz. We have certain components of the field strength, certain derivatives of phi, and maximum symmetric space. If we do that, there's an associated decomposition of our spinor parameter, the supersymmetry. So we start out with like a local Lorentz group, which is SO1.9, and this sort of breaking up here, there are associated groups with these 4D space, which is and 60 space, which are SO1.3 and SO6. And you can ask how the 16 representation, the spinor of SO1.9, transforms under each of these groups, how it transforms under say the local Lorentz group on the compact space X. And that's very easy to work out. It works like this. So you start with 16 supercharges. Under SO1.3, 4 of them, there are 4 sets of biospinors. Right? So you have 4 biospinors and 4 anti-biospinors, making a total of 16 components under the SO1.3 group. And these 4 biospinors get rotated into each other as the spinor representation of SO6, as you do a Lorentz transformation in the internal space. Okay. So that spinor splits up according to ansatz as well. And now we can just plug our ansatz into our, well, I'll probably refer to as Killing spinor equations, but into our supersymmetry transformations, and just see what we get. So one equation we have is the 4-dimensional component. This, yeah, the 4-dimensional component of the gravitino variation. And because I've set this flux with any leg in 4 dimensions to 0, this is just the Levi-Strauss connection of a maximum symmetric space acting on the 4D part of the spinor gives 0. Okay. But if I want to satisfy that, there's an instability condition. You can just form this object. That has to be 0, obviously. If this is 0, so is this. You just add this extra stuff and contracting. And you can find very simply that because of this sort of anti-commutational derivatives in here, if you play with it, you'll find that this implies that the curvature of 4D space-time is 0. So in other words, we've got a curvature 0 maximum symmetric space, so this is actually Minkowski space. Okay. So that's boring, but I could have just taken Minkowski space times X and ansatz in the first place. What do we have left? What are the killing spinor equations we have left? Well, first of all, we have the remaining components of the gravitino variation. So they look like, just writing out the same thing with a different index on that. Now we have the internal part of the spinor, equals 0. And of course the Dirac variation as well. And you can stop at this stage. And you can ask, what does this tell me about the manifold X? Right. So I want to preserve n equals 1 supersymmetry. So n equals 1 supersymmetry is one biospinor and one anti-biospinor of supercharges. So I want one each of these. Yeah. That Ricci scale. Oh, 4D. This is my writing, which is bad. So what I'm saying is 4D curvature is 0. Sorry. Please do ask questions, especially about my handwriting. So So what I'm saying is this equation applies to this in cosy space. Okay, so we want to preserve one each of these external Weyl spinors. So for this spinor, this 4 of SO6, this internal spinor, we want to preserve 1 out of 4 components. In other words, we want this equation to be true for 1 out of 4 components of the spinor. We want to preserve 4 to 6 symmetry. So what do we know about the manifold? What do we know about the structures in the manifold? Well, we know we have a single nowhere vanishing spinor on this manifold. Why do we know that? Well, we can parallel transport our spinor around with this connection, so it's a nowhere vanishing spinor. And a manifold, a 6 manifold, which admits a nowhere vanishing spinor, is said to emit an SU3 structure. So X emits an SU3 structure. So why is it called an SU3 structure? Well, just as a quick and dirty aside. So in general, the structure group of the frame model, if you like, but the set of transition functions that are patching together the orthonormal frames of the manifold are SO6 transformations. So a spinor on one patch of the manifold, and let's have it be the spinor that's a solution to these equations. There's only one such thing, so we'll just rearrange our bases of our spinor such that it appears in the bottom component of the form. In general, if you patch together a manifold, the transition functions acting on spinors lie in SO6 if it's a 6 manifold. So the spinor of SO6 is the fundamental of SU4. So in general, what you would have, if you go between patches, you would have your spinor on one patch, and to get the spinor on the next patch, you would have some SU4 matrix here, telling you how they're related. But I know I have this nowhere vanishing spinor, and I can choose to put it in this form on every patch. So this thing has to be everything the same form. And this type of form cannot be preserved with an SU4 matrix. If you have a general SU4 matrix here, in general, this only will be rotated up into the rest of the spinor. And in fact, the subgroup of SU4 that you can use while maintaining this form is essentially this. So you have a reduced structure group for the manifold to allow the existence of this spinor, and it's called an SU3 structure because that's what the transition functions are, roughly speaking. And this is a completely general thing. So if you looked at M theory on a 7-dimensional manifold, and you asked how do I preserve a certain amount of supersymmetry, what you would find is that the general answer is that instead of having SO7 structure, this thing would have to have some reduced structure. So if you wanted to preserve n equals 1, it would be G2. So that's just another group. So all you have to do is solve these equations of your manifold to find phi and h in the metric, and have a complete description of your supersymmetric background, and everything should be fine. The trouble is that is unbelievably hard in general. So finding non-trivial examples where you can actually solve these equations and find a background to the theory that preserves 4 supercharges is just difficult. So what do you do? Well, you do whatever you do when you hit a problem like that, you specialise even further. Okay, so the specialisation that's made, or often made, is to be really quite drastic. First of all, we're just going to set all components of h now to 0. That's clearly going to simplify things quite a lot, but it's also clearly quite drastic, right? Setting all this to 0. You also set phi to a constant. And you can see why these simplifications A are extreme, they really are extreme, but also why they help. If I set phi to a constant and h to 0, this equation becomes kind of easy to solve, right? This is 0 acting on the f ring, so this is actually solved for any of the 16 supercharges. So these two assumptions make the Gaussian variation 0 automatically. The Gravitino variation is also hugely simplified, and we just end up with the variation being the Levi-Civita derivative on the equals 0 for a quarter of the supersymmetry. So now, instead of manifold having to have SU3 holonomy, having a spinor that's covariantly constant with respect to some complicated connection, you just need a manifold that has a spinor that's covariantly constant with respect to the symmetric classical connection, if you like. And that means that the manifold, instead of just having SU3 structure, has SU3 holonomy. So I was asking this for starting PhD students, and when I started my PhD, I'm pretty sure I didn't know what holonomy was, so just to say very quickly, if you have a manifold, and you start with some vector, and you parallel transport it around some closed curve, in general, the vector won't come back to where you started. In general, it will come back, and you'll find that it's been rotated by some angle. If you look at all the curves that go from that point, then you get a bunch of different possible rotations depending on the curve you choose. And instead of all rotations is the group, and it's called the holonomy group. And in general, if you just pick some random manifold, some random metric field, you'll be able to get any rotation you like. And so in general, this will be SO6, just like the structure group is in general SO6. The fact that this spinor exists and is covariantly constant means that there is one spinor that no matter how you parallel transport it around the manifold stays the same. That's what covariantly constant means. And so the holonomy group must be reduced because there must be one spinor the holonomy group leaves alone. And so by the same argument we did up here, the full holonomy group is reduced from SO6 at SU4 to SU3, to the SU3 holonomy. Okay, why does this help us? It's not necessarily obvious, and it's in fact true, that it's not really any easier to find a solution for the metric to this equation than it is to find a solution to the metric in the B-field and the one up there. The point is that there is a theorem, which I'm not going to say exactly correctly, but good enough to say by Yao, which is the proof of conjecture by Calabi, which says that manifolds of SU3 holonomy, so if you like a manifold with a metric on it such that the parallel transport has this property, is one-to-one correspondence with Kähler manifolds. But the first Chern class of the tangent bundle vanishes. So a Kähler manifold is a manifold of UN holonomy, or you can think of it as just a manifold where you can, in complex coordinates, you can get metric from a double derivative of some function. And C1TX, well, we've heard a bit about what first Chern classes are today, but in graphic physics notation, you can also just think of it here as the cohomology class of the curvature 2 form, just the curvature 2 form. So what's the point? The point is that finding Ricci flat metrics, finding metrics that have SU3 holonomy on, say, this on a given manifold is going to be very, very hard, but we never need to do it. What we can do instead is find a Kähler manifold with a vanishing first Chern class, and we know then, thanks to this theorem, that even if we don't know what it is, that there is an appropriate solution somewhere on that manifold. You can put a metric on that manifold even if you don't know what it is. And even today, analytically, we don't know what the metric on Calabi-Yau we use is. We have no idea. Numerically now we do, to some extent. There are numerical methods for computing the metric on Calabi-Yau. But what we're going to use instead of trying to follow that path is we're going to use the algebraic geometry to actually describe some of the properties of this manifold that we need for the physics. You can't describe everything we need, but you can get a long way. So it's useful to characterise these manifolds in a different way than just it's a manifold with a covariantly constant spinor in it. You can build forms out of your spinor instead and describe the manifold with those forms. This is going to be useful to us later on. So I'll just mention it here. By the way, there should be more questions. We're building it slowly, so maybe people know this, but people should stop me and ask them. So you can build a 2-form out of this spinor that's covariantly constant, this preserved supersymmetry, just by sandwiching some gamma matrices between it and its object. And likewise, you can form a 3-form, just to leave it up, which has a real part and an imaginary part. And then you define omega to be omega plus I omega minus. And when you do this, you can characterise the structure of the manifold instead of by what this spinor looks like, by what these forms look like instead. So in particular, if you just play around with gamma matrix algebra, you'll be able to prove the following relation. Sorry? My omega? Sorry. So if you take J, if you take J and you actually give it 2 copies of it, if you just play around with the gamma matrix algebra, you can show that that's going to be omega which omega bar. You can show that J is equal to 0. And these relations, you can do something very similar for the case of SG3 structure, for the case where instead of this being true, this is true. So in this case, we would also have a spinor. We could also sandwich that spinor on either side of gamma matrices. We could make these same forms or analogous forms, and they would still have these properties. It's just, I'm not using the fact of what this derivative is. This is just some derivative acting on a spinor. I'm just using that spinor, whatever it is, and sandwiching it between gamma matrices, on either side of gamma matrices. However, there are other properties that do change. So, for example, in the Calabi-Yau space case, these spinors are covariantly constant, and that means that d omega and dj are going to be 0, right? Because it's a compatible connection, and the derivative acting on these are 0. So if I calculate these d's with that connection, then I'll get a matching answer. In the case of a more general manifold SG3 structure, these two things would not necessarily be 0. You would have something on the right-hand side. And so you can think of, if you like, the specialisation that we're making in allowing ourselves to use this algebraic geometry, it's insisting that omega and j are closed. Okay, so I've been saying as we go along that we make this specialisation. Yeah. No, it's got 3 indices, and you're working in 6 space. Yeah, it's actually, you're right in that it's actually, I guess you're imagining it's a holomorphic form, which it is, but then you've still got 3 complex coordinates, so you're still okay. It's a top form, so it's kind of unique, but upscale, but you're still okay on the metric grounds. This is a real expression, so, well, I could have, for example, 3 complex indices and 1 non-complex also. Yeah, you could do that, but also, I mean, this doesn't have to be 0, right, because it could be a 1,3 form. Actually, in the SG3 structure case, you have to be really careful. So when you've got a complex manifold, everything's great, and you can say, this is a 3 form, not 3 form, say, so this has to be a 1,3 form. But if it's not a complex structure, it's an almost complex manifold, then things get more complicated. This could be a 2,2 form, things get weird. But we're going to concentrate on this case, so everything's okay, it's 0. It doesn't have to be 0 if you're unhappy. Good. Any other? Okay. What was I going to do? Yeah, so I've been saying that we're going to be able to describe these Calabi-Yaus with algebraic varieties, and indeed we will. We'll see that as a concrete thing in a few minutes. But how do I know that we can't use algebraic geometry and all the other stuff? How do I know that in the other manifolds of SG3 structure, I can't use algebraic geometry as well? And you have to be careful about how strong a statement you make here. I mean, there are certain SG3 structure spaces that are not Calabi-Yau, which you can use algebraic geometry to decide certain properties of. However, the following is true, and it gives you an idea of what the problem is. So you can say, which of these manifolds, so which of these solutions to our string theory, is a projective variety? So which of them could be described as the vanishing locus of a polynomial in projective space? Single or multiple polynomial equations in projective space. Well, what would we know about such a manifold? Well, we would know that if we use the nice complex structure in projective space, we would know that this projective variety is Kähler, because projective space itself is Kähler. There's a known Kähler form of projective space, it's the Fubini-Stuck metric. If you just restrict that to your projective space, then inside you have your manifold living. If you just restrict the Kähler form on the ambient space, it's called projective space, to the manifold projective variety living inside it, you get another Kähler form on the variety, so we know that this is Kähler complex. What else do we know? Well, we know we have this 3 form, which, as I said, is holomorphic, so depending on which way around you do it, you can regard it as having 3 barred or 3 unbarred indices with respect to the complex coordinates on the manifold. So we have a nowhere vanishing 3 form, so not 3 form. It's nowhere vanishing because remember this spinor doesn't vanish anywhere in the gamma matrices. So we've got a nowhere vanishing not 3 form, and that, a not 3 form, like that, is a section of the third wedge power of the cotangent bundle. Right? An element cotangent bundle is just a second cotangent bundle, which is 1 form. This is the antisymmetric product 3 times, so I get a 3 form. So I have a nowhere vanishing section with the third wedge power of Tx star. The third wedge power of Tx star is the top wedge power, so this is a line bundle, so this is a rank 1 object. There's only one holomorphic not 3 form up to scale, so this is a line bundle. And the only line bundle that has a nowhere vanishing section is the trivial bundle. Okay. So, the fibre direct product with the base space. So what all of this means is that C1 of wedge 3 Tx star, whatever our surface is the same as C1 of the trivial bundle, which is 0. But C1 of wedge 3 star, there's sort of rules for how we C1 behave under wedging and so forth. This turns out to be the same as minus C1 of Tx, the first Chern class of the tangent bundle itself. So that's 0 as well. In all the arguments, it doesn't matter. The point is this: if you want to describe one of these SG3 structure spaces as a projective variety, then it's going to be a manifold which is Kähler and has vanishing first Chern class. And that's Calabi-Yau. So you're stuck. Right? If you want to describe these more complicated spaces as algebraic varieties, something in the rubber dodgy argument I gave would have to go wrong. Okay, so we're going to look at being careful not to take these statements we've made too seriously in a second. But I just want to say something about how general these arguments are, about solving Killing spinor equations, looking at what kind of derivative operator you have with a covariantly constant spinor with respect to it, and how algebraic varieties arise. This is a completely sort of general type of thing in string theory. So if I took, instead of heterotic string theory, type 2 string theory, and I said the same thing, you'll hear people say, I'm going to add extra words like oriental, but they'll say things like, I'm going to compact my type 2 string theory on a Calabi-Yau, so I end up with n equals 2 supersymmetry in 4 dimensions. What are they doing? They're doing exactly the same analysis. They're writing out the supersymmetry transformations in that case. There's one extra spinor there, that's why they get 2 supersymmetries and not 1. But then they'll follow through exactly the same analysis, ask how they solve those Killing spinor equations, make the same specializations from a general structure to a special holonomy. And then, when they've done all of that, they'll get to very similar conclusions that they can describe their Calabi-Yau as an algebraic variety and so forth. Another thing people will say is, I have branes in my setup, so I have my manifolds. So imagine now this is the Calabi-Yau, and then I'm wrapping some D-brane around a cycle, some extended object around a cycle in the Calabi-Yau. They'll say, if you preserve supersymmetry, I take my space to be a Calabi-Yau and my D-brane to wrap a holomorphic cycle. So how did they get this information? How did they know what the D-brane had to wrap to preserve supersymmetry? Well, they just do exactly the same type of calculation. You would have a 10-dimensional action on your original space-time, just as we did, but then you would also have some dimensional action depending on the size of your D-brane for people just living on the extended object. That's going to be a supersymmetric theory. They'll have fermionic variations. You'll do a similar type of story. Ask when do those fermionic variations give you 0, when do you preserve supersymmetry, and you'll find it's when the cycle is holomorphic, if that's what they're telling you the answer is. So this is a really general thing. You can get a long way, and often the reason algebraic geometry comes into string theory is because of preserving supersymmetry. I should say another reason it comes in is that moduli spaces are often vacuum spaces, if you like, are often algebraic varieties. And one reason of seeing why that may be true is you know that the n equals 1 supersymmetric theories have a Kähler manifold as their field space. So if you're talking about vacuums inside a Kähler space, then there's a chance it's going to be an algebraic variety. We'll see more of that in the third lecture. Okay. So this is the general picture, and before I knock any holes in it, does anyone want to ask anything else? Yeah. There are certainly non-supersymmetric vector here. Yeah, I see. Yeah, there's certainly supersymmetric vector here that are non-Kähler too. Right? These are these SU3 structure cases that we looked at. In general, these won't be Kähler manifolds. In general, they're not even complex. Right? But all I was giving with the Calabi, and all of that will happen in type 2 as well. So there's these special structure manifolds which are really general. They can be many different types of things, but of course you've got very few tools to deal with them. That's the case you'd really like to attack. Right? That's the general problem. But then we make these specializations because basically we don't know what we're doing there. So then we make a specialization where we can deal with the manifold, and that's where the algebraic geometry comes in. Yeah, thanks. People make too strong statements about this sort of thing, and this is particularly relevant in my field of string phenomenology, where people will try to claim you have to look at a certain type of manifold because of this kind of argument, which is not true. So I just want to say a few words about that before we move on to talk a little bit about F-theory. So this is just an aside about be careful what you state. So here's a statement that someone might make that on the sound of it, the face of it sounds reasonable. They may say without flux, so if h equals 0 and phi equals constant, then you must compactify on a Calabi-Yau threefold, something like that, to get an n equals 1 theory in 4 dimensions. So this is a statement that people will make, and on the face of it this looks reasonable, isn't this what I just said? Right? We had this general case, and I specialised in the case where h was 0 and phi was constant, and we got a Calabi-Yau threefold. So why is this in fact not quite true? The reason it's not quite true, and this may seem like a pedantic point, but I'll explain why it's important in a minute, is that there's a difference between the amount of supersymmetry of a theory and the amount of supersymmetry of its solution. Right? So what we just showed is that the solution of this 10-dimensional theory, if it's going to preserve n equals 1 supersymmetry, then the space would have to be a Calabi-Yau. But you can do something more general, and let's have a look at what that is. So there's a really nice discussion of this in a paper by Dan Waterman and his collaborators, which I recommend if you read nothing else, just read the introduction of this paper. It will change the way you think about this type of stuff. And the example I'm going to give you is by Lucas and Matti, and they presented this example, and many others, in this paper. So what are we going to do differently? Well, we're going to change the ansatz we had at the start. And instead of asking to preserve n equals 1, we're going to ask initially to preserve n equals a half supersymmetry. Now this may seem like a crazy thing to do because n equals a half supersymmetry, especially if you're doing phenomenology, is no good to anyone. But let's just do it and see what we get. So we're going to make ansatz. The metric this time, we'll still set phi and h to 0 just for simplicity, phi to a constant. But we'll take the 10-dimensional space-time to be a 3-dimensional Minkowski metric, not 4. One extra dimension with a sort of a warp factor out the front of it. It looks like this. I'll explain what this is in a second. And then a manifold of SU3 structure. dxu, dx0 here. This is a function of xi2. So what I mean by these xi's is this metric is a function of the 6-dimensional space and this y coordinate. This coefficient out the front here, which actually doesn't matter very much in this case, but this coefficient out the front here is a function of y and of this 6-dimensional space. You can pretty much forget about that coefficient. And what you can do is you can say, given this set, this ansatz, and given that instead of preserving 4 supercharges, I just want to preserve 2, n equals a half. Do the same analysis, see what you get. And we can write those forms we had, my poorly written omega and j, and you can write them in this case, and you can ask, what sort of relations do they obey? They can obey this omega wedge is j wedge j wedge j, they can obey j wedge omega equals 0, but what about the differential bits, the bit that was 0 for Calabi-Yau? So you find in this case that d omega minus is still equal to 0. Right, the imaginary part is still 0. You find this equation, which is still looking good. But you also find the following. The y derivative of j appears and gives you a non-zero d omega plus, so it's not closed anymore. There's also the stereo derivative of this thing appearing. And similarly, dj is not 0 anymore either. Okay, so note that if I took away all the y dependence, so I made this basically called the Minkowski space again, and this became naught, so this was just, as I said, the Minkowski space, this would all vanish and you get back to the Calabi-Yau case. But if you allow yourself to preserve n equals half of the solution, rather than n equals 1, this SU3 structure can be something else. It doesn't have to be a Calabi-Yau, it can be something more general. Why do you care? Well, you can do the following thing. How is this going to give you an n equals 1 theory? So what we're going to do is we're going to find an n equals 1 theory in 4 dimensions, which doesn't have a Minkowski space ground state. Instead, it's going to have a ground state that's a domain wall solution that varies in one direction, and that's going to be this. So what you do is when you do the dimensional reduction, is you keep complete n equals 1 multiplets in the dimensional reduction. What do I mean by that? Well, you've got this SU3 structure space, and that picks out a particular spinner. Right? When we do the spinner decomposition and we've got this 2, 4 plus 2 bar, 4 bar, it picks out a particular vial spinner and a particular anti-vial spinner by choosing an element of the 4. So what you do is when you do your dimensional reduction, if you keep a given field, you keep anything that's related to it by one of those supersymmetry transformations. Right? You keep complete multiplets under this n equals 1 supersymmetry, and when you do that, you're guaranteed to get an n equals 1 theory. Right? Just the original action is invariant under that symmetry, you're keeping everything that gets muddled into everything else under the symmetry, the action will still be n equals 1. So what goes wrong, because this only preserves n equals a half? Well, like I said, the vacuum will be an n equals a half solution. And when you look at what the n equals a half solution looks like, it's exactly the four-dimensional manifestation of this domain wall solution. So you can compactify it on a manifold of SU3 structure, rather than a more general manifold of SU3 structure, not just on a club Yow, and you can get an n equals 1 theory. It's just that it won't have an inconstant space vacuum, it will have a domain wall. Yeah?
Can we keep just the one
Yeah, because when we do this 16, decomposes as 2, 4 plus 2, 4 bar. Okay? 1/4 of the supersymmetry, so n equals 1 supersymmetry, is keeping one of those and one of those. The SU3 structure picks out one covariant constant spinner on the internal manifold and one anti. And so that's the spinner that you keep the complete multiplets of, and so the n equals 1, your theory in four dimensions will be n equals 1. If you kept everything, if you kept all three defined states of everything, then the theory would have as much supersymmetry as the theory you started with. It would just look weird. But if you just keep complete multiplets under this particular n equals 1 supersymmetry that's picked out, it will be an n equals 1 theory. But the vacuum, as I said, will be n equals half. And in this paper, they actually give you the theory. They give the superpotential. They find the solution for the vacuum in this theory, the supersymmetric vacuum, and they show that the two agree. So what's going on here? Well, let's have a maths what's going on and physics what's going on. Or maths what's going on and physics, I still don't see why I care. So the maths of what's going on is I have this y direction, this extra direction in four-dimensional space, which is sort of split off from my three directions where something's varying. In particular, if I look at the SU3 structure manifold over this direction, it changes as I go along this direction. And what's happening, the reason you're getting an n equals a half solution here, is that this direction, together with this 6-dimensional manifold, forms a 7-dimensional manifold. And that 7-dimensional manifold has SU3 holonomy, has G2 holonomy. So these are basically a very slight generalization of something called Hitchin's flow equations. And what this does is tell you how to take an SU3 structure guy and fibre it over a line to get something of G2 holonomy. No, it's not compact, because this y direction is one of our four-dimensional space directions. Good question. Yeah, but it is still got G2 holonomy. And this is going to shoot my next dodgy argument in, but if you imagined, even though it's not compact, if you imagined hiding those extra dimensions, right, then the same sort of argument that says that if you compactify to 4D you need SU3 structure, SU3 holonomy, the same sort of arguments would tell you that this ought to be G2 holonomy if I don't have any H or any phi, which I didn't. Okay, so basically this is, all I'm trying to say is if you combine the 6-dimensional manifold with a line, this is basically Hitchin flow, something called Hitchin flow. You're building manifolds of a G2 holonomy in 7 dimensions. If you went for a more complicated thing and put the flux back in and all that sort of stuff, you get some big generalization of Hitchin flow, where this is some manifold of G2 structure. That's the idea. And they do more complicated cases in the literature. Physics-wise, why do we care still? If I looked at this 4D theory, there would be a vacuum solution where one spatial direction had all the fields varying, and we live in Minkowski space. So if I was trying to use this phenomenology, I would care. Well, when people are using these kinds of compactifications, they add in all sorts of effects beyond the sorts of perturbative physics we've just used. So when they're trying to do things like stabilized moduli, you may have heard of the KKLT scenario and all this sort of stuff, they'll add in lots of non-perturbative effects from instant brains wrapping cycles and Gaugino condensation, all these sorts of non-perturbative effects. And what you want is some kind of Minkowski vacuum after you've added all that back in. Right? You don't necessarily need it to be Minkowski at the perturbative level. In fact, yeah, well, KKLT wasn't in type 2b, that would be an example of that. There is a lot of problems with this kind of approach. In general, there's only one energy scale in the problem, which is the size of the compact manifold. So in general, the variation here will be a variation with sort of an energy scale at the compactification scale, and so you shouldn't really be describing this in 4D theory in the first place. It's a very violent behaviour. But you may be able to tune it, and this is what these people try and do, you may be able to tune it so that this variation is very slight and can still be treated in a 4D context. Okay, I'm just mentioning that because that sort of thing's becoming popular in the literature right now. Let's skip on something more solid. Let's just talk about one other way in which algebraic varieties appear in string theory, which on the face of it looks nothing like what I've been talking about. Unless there's any other questions. So I'm sure more qualified people than me are going to talk about F-theory in this series of lectures, but I'm just going to give a very rudimentary introduction to F-theory just so that we can look at the conditions people talk about preserving supersymmetry and why that gives rise to algebraic varieties. So it's going to look like a different thing on the face of it, but it's going to turn out to be the same kind of argument. So what is F-theory? So in 2B string theory, and just one of the other string theories, there is a scalar field called the Axial dilaton, which looks like, is often called tau, and it just looks like this. It's the scalar field we had earlier, essentially, and something called the Ramon naught form. So it's just some scalar field, it's just some scalar field in theory, and often what you're interested in is solutions to the theory where the scalar field varies. And what people do is they describe this scalar field as a complex structure of a two drops. So if you have just a complex plane, you have a coordinate on it, and you just make the usual identifications. Oops. So you have two complex numbers, number 1 and number 2. You identify under integer multiples those two complex numbers. Then the complex structure of this torus is just lambda 2 over lambda 1, which better not be real, right? I mean, these two vectors better not point in the same direction. If you want the torus to be right. And there are many reasons why people use, so what they do is they have a 10-dimensional space-time, and everywhere over the 10-dimensional space-time they imagine having this torus. And the complex structure of this torus varies over the 10-dimensional space-time, and how it varies is supposed to describe the scalar field. And there's many reasons why you would describe a scalar field like that. One of the main ones is there's singularities which are essentially sources to this field, and they correspond nicely, the physical singularities you get correspond nicely to the ways in which the to 4 dimensions on a 6 manifold, which together with the torus is going to make an 8 manifold. And what people will say is the following kind of statement. They'll say that F theory on a Calabi-Yau fourfold gives rise to an n equals 1 theory in 4 dimensions. So what they mean is this 6-dimensional base with this torus over it combined as a complex 4 manifold or as an 8 manifold is a Calabi-Yau fourfold, and then you preserve n equals 1 supersymmetry. And on the face of it, that looks like it must come from a very different argument from the type we've been using. What we've been saying is, what you do is you look at the action on now this 12-dimensional space, and then you vary the fermions and you see what supersymmetry. But you don't have a 12-dimensional action here, right? There's no 12-dimensional action of F theory. This torus is just a trick for describing a scalar field, essentially. So where does this statement come from? What is this? Well, what you do is you use some dualities. Basically, there's never that many ideas in physics, right? So you relate the case you don't have to do back to a case that looks the same as when you do. So what we do is we use some dualities to relate this statement back to somewhere where we can do our usual analysis of a Killing spinor equation and get a solution. So the two dualities we're going to use are the M theory. So this is the 11-dimensional theory on a circle. Is by S duality the same thing as type 2A string theory. Okay, and in fact, the type 2A coupling is representing just the radius of the circle over the string length. So if you take this circle, if you take 11-dimensional space time to be a circle times something, if you take the circle to zero size, you go back to weakly coupled to a string theory. So how do people know this? Well, there's a nice description of this in a paper by Whitman called String Theory in Various Dimensions, I think. And what they do, the way they see that this is true, is there's certain states in type 2A string theory which are BPS, they're symmetric and they're protected, and certain quantities are protected against making corrections. At least postulated. So what you do is you take those states, you look at the spectrum, and then you take the limit that the coupling goes large. You believe your results still because of this protection, and what you see is the Kaluza-Klein tower of a reduction of M theory on S1. So there's some duality that relates M theory on S1 to just type 2, where the S1 has disappeared. There's also T duality, which relates type 2A theory on an S1 to 2B on S1. This is just some canonical change of variables and worldsheet. And when you do that, the 2B coupling is given by the 2A coupling over the radius of the circle. And so the idea to get from F theory is to get from M theory to F theory using these dualities. And what you do is you just combine the two circles and you make these our torus directions. Okay? So I'm just going to do it for a square torus because it avoids me having to think about form fields. So I'm going to say that M theory on a square T2 times something is the same as 2B on just that something times R. So what I'm doing, we're taking these T2s, one direction is this circle, one direction is this circle, and I just shrink the size of the torus to 0. And as I do that, as this direction shrinks, I go to 2A string theory with this coupling, and when I shrink this circle, I go to 2B string theory with this coupling. So the final 2B coupling. Thank you. Thank you. Okay, so take the limit x goes to infinity. Thank you. Yeah. So the 2B coupling in this case is 2A coupling LS over RT, which is just from the formula here, it's going to be RS over RT, the ratio of the size of these two circles, but that is the complex structure, at least the imaginary part, because it's square torus, the imaginary part of the complex structure of that torus. Okay. So if you take M theory on T2 and you squeeze it down, you get 2B theory on this space, and if you squeeze this torus to zero size, this will go and become half of this one. Where the complex structure of the torus gives this field profile, so that's F theory. Okay, so what do we do now? Well, now we want to compactify, instead of just having a direct product here, we want to compactify on some non-trivial manifold and get down to a 4-dimensional theory. So what you do instead is you fiber T2 over M3 times 6, M6. So you take M theory on a T2 fibration over this 6-dimensional manifold times a 3-dimensional manifold, and you do the same set of dualities. And just because if you look on the 6-dimensional manifold, locally the fibration always looks trivial, you get, the argument is that they call it the adiabatic approximation, but you can do the same set of dualities, and what you'll get is instead of 2B on, when you take the limit flat space, you'll get 2B on M6 with this torus, the F theory torus fibered over in the same way. Okay, so how does all of this help us with supersymmetry? Well, the idea is this. I want to know why this T2 fibration over the 6-dimensional space should be Calabi-Yau fourfold. What I do is I look at M theory, 11-dimensional theory, on that Calabi-Yau fourfold compactifying down to 3 dimensions. There is an action. There is some way we can do the calculation, and we can work out the theory with a certain amount of supersymmetry you get. In fact, Michael Wivian Louis worked this out with the flux design, for example. You can actually do the calculation and work out how much supersymmetry you can preserve. But according to duality, this is the same as F theory on the same space. So you use the same techniques, but using dualities to relate the case to relate the statement about supersymmetry to a case where you actually have an action. Okay, so finally that's all I'm going to say about preserving supersymmetry. And we're just going to go on to briefly meet that. So today has been quite wordy, we've just been talking about why you're interested in algebraic geometry, where it comes from, how general these techniques of solving Killing spinor equations are. Tomorrow we're actually going to go on to start doing some proper calculations. And when we do that, we're going to be working on examples of Calabi-Yau threefolds. So I'm just going to introduce the examples of Calabi-Yau threefolds we're going to be working on, so that we're ready to talk about vector bundles tomorrow, which is what we'll go on to. So how to choose a set of Calabi-Yau threefolds to work on, to give examples that are going to be giving you an idea of what goes on in the subject as a whole. So it's pretty difficult, but I've decided that we're going to, partly because they're again things I work with every day, we're going to use a set of Calabi-Yau threefolds called complete intersections in products of projective space. Now this is a very small, really, projective. So this is a very small set of Calabi-Yau manifolds. There's only some 7,000 of them. But they have some nice features. One is that it's a big enough set that you see lots of different types of structure in there, which we'll see. Another is that they illustrate the general principles of how people often describe Calabi-Yaus on this subject. And in particular, the technology that we'll develop to calculate things on these Calabi-Yau threefolds directly applies as well to the biggest set of Calabi-Yaus known, the hypersurfaces and toric ambient spaces. So you can learn a lot by studying these simple cases. They're a lot simpler to deal with than torics, but you learn the techniques that you need to know. And to introduce what these are, it's easiest to give an example. So these are completely classified, the manifolds are known, and they're determined by a matrix, or they're written as a matrix which looks, for example, like the following. This is called the bicubic. And this matrix defines a Calabi-Yau threefold. So what do we have here? Well, the basic idea of this construction is that, as with all our great varieties, you're going to describe your complicated Calabi-Yau manifold and have some calculation control by embedding it in something simpler. Right? The simpler thing is called the ambient space, and the ambient space here is just going to be a direct product of P2 times P2. And that's what this first column is. So we have our ambient space. And as we were hearing today, we're going to describe the variety inside this by the vanishing locus of a homogeneous polynomial in the homogeneous coordinates of these projected spaces. So we have the vanishing locus of some polynomial, as the Calabi-Yau. And this is determined, what the polynomial is determined by this column. So the idea is that the Calabi-Yau is the vanishing locus of a bicubic polynomial. So the way it works is each time you have a column, the numbers here give you the degree of the polynomial in the homogeneous coordinates of the associated ambient space. So another example would be, if I wrote down a manifold called the quintic, this is defined by a quintic polynomial in the homogeneous coordinates of P4 and where that vanishes. So in general, you can have several products in your ambient space, so this can go on and on, and you have to define the degree of the polynomial in each piece of the ambient space. In general as well, you can have more than one equation. So the Calabi-Yau manifold can be the intersection of two polynomial equations if you start with the ambient space. And if that's the case, if there was more p's here and there's more than one equation, you just have several columns, one for each equation. So like I say, there's some rules for when these things are Calabi-Yau, which we'll see next time, and you can just go through and classify these. What else do we have here? Well, we have this, and we have this number. What are these? Well, these are the number of harmonic H11 forms, 11 forms, and the number of harmonic 12 forms on the manifold. And again, we'll know how to calculate these next time. So these are H11 and H12. And we're actually going to consider a special type of complete intersection Calabi-Yau that has a special property. It's very much linked to its ambient space. It has extra detail that you can gain about the Calabi-Yau living inside the ambient space because of a property called favourability. So as always, there are several different definitions of favourability in the physics literature. So I'm going to tell you which one I'm using and be careful not to be confused. So what I mean by that is that H11 of this manifold is 2. And there is 2 projected spaces. Now I can get one harmonic form on this manifold by restricting essentially the Kähler form of this P2 to the surface. I can get another one by restricting the Kähler form of this P2. But that completely gives me a basis of my harmonic 11 forms on this manifold. So very roughly, favourability means that all the harmonic 11 forms descend from the ambient space. We will see when we start writing sequences up what that really means next time. But the thing I want to leave you with is, again, the way you deal with these manifolds is having them embedded inside something simple. The reason that this is a useful property is it's another property of the Calabi-Yau that's directly coming from the ambient space. Okay. So I keep telling you this is a Calabi-Yau. Why should you believe me? How do you know that this is a Calabi-Yau manifold? So what we're going to do is we're going to do the really stupid way of figuring out this is a Calabi-Yau manifold today. And I suggest you try it at home. And then tomorrow we'll do the sensible way of proving this is a Calabi-Yau manifold using the algebraic geometry. And then you'll see why algebraic geometry is a good thing, because you'll see how much work it's saving you. I really sold you doing that calculation, didn't I? Okay, so how do we know this is a Calabi-Yau manifold? Well, here's the stupid way of seeing this. Okay, what do we need? We need it to be Kähler. Yeah. And we need C1 of Tx to be 0. Okay, this is clearly Kähler. I mean, it's a complex submanifold of a Kähler manifold. Just restrict the Kähler form. This is a Kähler manifold, so this one's okay. What about C1Tx? Well, this is the cohomology class of the trace of the codec 2 forms, is it? So this is something that basically you need the metric to work out. So you may think, well, there we're stuck. I have no idea what the Ricci flat metric is on this space. We know metrics on P2 times P2. There's the Fubini-Study metric. Right? So we could take the Fubini-Study metric and we could restrict it to the Calabi-Yau, but that's not the Ricci flat metric. That's not the metric with SU3 holonomy. So how am I going to calculate C1Tx? Well, we're going to use the fact that it doesn't matter for given complex structures. It doesn't matter which metric you calculate this with. It always gives the same answer. So if you take the metric, the Fubini-Study metric on P2 times P2, restrict it to say the bicubic hypersurface inside P2 times P2. If you then work out the trace of the curvature 2 form, you should be able to write that as a total derivative. You can do it. It works. I haven't actually done it for the 3-3. I've done it for the quintic. It works. So that means that just by knowing about how this surface lives in the ambient space, we'll be able to figure out these Calabi-Yau. We'll find a much better way of doing that tomorrow that doesn't involve all this differential geometry stuff, and that will be very helpful. So I'll just say a couple more things. So first of all, we can already see some moduli of the Calabi-Yau, and this will be an important thing for us tomorrow. Or actually, yeah, tomorrow in the third lecture. So, structure. So we have this defining polynomial, P, which tells us where the Calabi-Yau is in the ambient space. And P is just sum over terms of coefficients of all the possible polynomials which are cubic in both the coordinates of both homogeneous coordinates of both P2s. So schematically, these monomials are something of the form x cubed, y cubed, where x1, x2 squared, and so where x is the homogeneous coordinates of this P2 and y is the homogeneous coordinates of this P2. But you can see, all I've specified in giving the Calabi-Yau is the degrees. I haven't actually given you an actual polynomial. And as I change these coefficients, this guy is going to move around inside the ambient space. But all you need for it to be Calabi-Yau is that the degrees are right. So these are moduli, right? If you change these coefficients, the Calabi-Yau will move and morph and change, but it will still preserve supersymmetry. It will still be supersymmetric. So these are, in fact, a redundant description of the complex structure moduli. Why are they redundant? Well, again, we'll see this properly tomorrow when we do vector bundles and particularly look at what the tangent bundle of this thing looks like. But they're redundant because, for example, if you imagine scaling all of these coefficients in the same way, multiplied more by 2, you don't change what the zero locus of the polynomial is. So it's clear that the overall scale of the polynomial won't move the Calabi-Yau. Right? I can just put a scale up front here and it has the same solution for p equals 0. So it's clear that while these are a set of moduli per theory, that they're a redundant description of those set of moduli. And exactly how you get back to the proper description we'll see tomorrow. In fact, this is supposed to be the number of complex structure of the Calabi-Yau. And if you work out the number of bicubic monomials, you find out there are many, many more. So that's this redundancy. Okay, last comment I'll make. Here we've been talking about threefolds, but the same construction of Calabi-Yau can be used to construct Calabi-Yau fourfolds for use in F-theory. So let's just have a 5-second look at that. So, the Columbia four folds are not